Hello, I'm Cameron Smurl, and today I'm going to cover how to solve second order homogeneous equations. So let me get my annotate tool out. Let's see, draw. So here is a second order homogeneous equation. You have three constants connected to the second derivative of y, the first derivative of y, and then the original equation y. And the reason why it's homogeneous is because it, this equation is set equal to 0. And yeah, so basically, since each element is a constant multiple of the first and second derivative, oh yeah, we use e to the rt because since each one of these is just a constant multiple of the previous derivative of that y equation, you need to use e to the rt because when you derive e to the rt, it's simply a multiple of y. So y prime, the derivative of e to the rt is r times e to the rt, which boils down to ry. And the same thing with, I don't know why this is not move out of my way. Anyway, same thing with the second derivative. It's r squared y. So once you plug in e to the rt for y, you can basically get rid of e to the rt because, or you can factor out e to the rt because it's a common denominator or common multiple of it, and then you can cancel it out because e to the rt, or you can divide it out because e to the rt will never be equal to 0, and you're left with a times r squared plus br plus c is equal to 0. Then, and next we get to the three different types of roots that you can get once you get boiled down your original second order differential equation to this. You solve it just like you would any normal quadratic equation by either factoring or using the quadratic equation. The three possible roots that you're going to have are discrete roots. So, this is what we learned in, I don't even know, sixth grade maybe. You just factor it out, and r is going to be equal to -3/2, and then r is also going to be equal to 2/3. Next one we're going to have is repeating roots, and that is when, and in this case, r is equal to -5 when you factor this both times. And then we have complex roots, which involves imaginary numbers, so I, because you can't take the square root of a negative number without having I in it. And for each one of these, we have different methods to solve that second order differential equation, and we're going to go over how to do each one of these. First is discrete roots. This is pretty simple. You convert the second order differential equation to what we talked about using e to the rt, and this converts pretty simply to 6r squared plus 5r minus 6 equals 0. Then once you factor that, I'm going to be using all the same equations as in this slide as well, just to keep things simpler. And you factor this out, you get both the r values, and then you plug in these r values to e to the rt, and then you plug them into the equation y equals c1. You have c1 and c2 for just constants, and this is the answer, or this is the solution to this second order differential equation. And here's a proof. I'll move my camera a little bit. If you plug in this e to the 2/3 t into the original equation, so you just take the derivative of y and you plug all this in, and it all boils down to 0 equals 0, which obviously is true. So, and that works for either one of these values. I just kept it simple and plugged in one just for an example. Okay, so next we have repeating roots, and again, I'm using the same equation that I factored a couple slides ago, and r is equal to -5 in both cases. But you can't simply set y equal to c1 e to the -5t plus c2 e to the -5t, because each one of these has to be linearly independent of each other. So Instead, for the second one, we use a function of time v of t, and then we plug this into this original equation, and that you use reduction of orders for that, and you take the derivative of v times e to the negative 5t, and then take the second order derivative of that, and then once you plug all that into this original equation and you simplify, it boils down to c2t e to the negative 5t. And I could have written out all this stuff, but it's simple algebra, just cancellations and everything. And then you take this, you put that there, and you take just the, basic one with, and also right there. That takes a long time. I did all of that. I did all the algebra, and it was kind of a pain. So you can also use the shortcut, which is Rn is equal to t to the n minus 1 e to the RT. So as you can see, this is n equals 2. So t to the 1, e to the r, and r in this case is negative 5t. So that'll save you a lot of time. Next, we have complex roots, and for this we use r is equal to alpha plus beta I. So we plug in r in our original e to the RT, and that gives us e to the beta t times e to the I beta t. And we can use Euler's formula, which is e to the I theta is equal to cosine theta plus I sine theta. And we can plug this in and into e to the RT. And that gives us e to the alpha t times cosine beta t plus I sine beta t. And once you distribute this e to the alpha t across, you get this right here, e to the alpha t cosine beta t plus I e alpha to the t, or e to the alpha t sine beta t. And then you can use both of these parts, these individual parts, to find your solution. Here's an example that I wrote up, and this is from one of the first slides. So you get this, or you have this equation, you convert it to this quadratic, then you use the quadratic formula, and that'll give you 1 plus or minus 3i. And once you get this root right here, you simply just plug in 1 for alpha and 3 for beta, and this into both of these, and that'll give you your solution right here.